January 1942. Inside Boeing Plant 2 in Seattle, the mood wasn't patriotic or confident, or anything you'd expect from America's biggest bomber factory in the middle of a world war. It felt stuck, like the whole building had locked up. 63 unfinished B-17 flying fortresses sat frozen on the assembly line. 63 metal reminders that the United States had made a promise it absolutely could not keep. The Army Air Forces hadn't been vague about what they needed. They wanted 3,115 bombers delivered in 1942. Boeing had delivered 9. Not 9 per week, not 9 per month, 9 total. And furious doesn't even begin to describe how General Henry Hap Arnold reacted. On January 15th, he stormed into a meeting with Boeing executives and made it painfully clear. If America didn't get bombers, they didn't get a strategic bombing campaign. And without a strategic bombing campaign, the only way to defeat Nazi Germany was by sending hundreds of thousands more soldiers straight into a fortified war machine. It wasn't a manpower problem. Boeing had hired 30,000 new workers in half a year, many of them women who'd never touched industrial tools until the war began. It wasn't a materials problem either. Alcoa was shipping aluminum to Boeing faster than workers could rivet it into place. The true crisis was the last thing anyone expected. The bombers themselves were too complicated to build. A B-17G had around 140,000 individual parts. Just the wings required 12,000 rivets per side, layered through 7 sheets of aluminum skin over an internal skeleton built to survive up to 6 Gs of combat stress. Before the war, Boeing could take its time on smaller aircraft, smoothing out inefficiencies with careful craftsmanship. But that approach collapsed under the B-17's sheer complexity. Every morning at 5 a.m., production manager Philip Johnson walked the factory floor, clipboard in hand, jaw tight. And every morning he saw the same thing. Wing Assembly Station Number 4 choking the entire line. 17 workers trying to crowd around a single wing section. One riveter stepping back so another could squeeze in. Hoses tangling, tools clashing, inspectors climbing over half-finished work. It wasn't a workflow, it was industrial bumper cars. He timed it himself. 20 hours and 14 minutes. That's how long it took to assemble one wing section. 20 hours for a single wing. Meanwhile, Britain was losing bombers faster than that, in the skies over Europe. Every day the U.S. fell behind schedule meant more Allied convoys torn apart in the Atlantic, more German factories running at max capacity, and more time for Hitler to reinforce his fortress Europe. Boeing tried everything. Redesigned jigs, new tool stations, more workers, fewer workers. Nothing mattered. The problem lived inside the engineering blueprint itself. The rivet pattern, which looked elegant on paper, forced crews to work in a strict, overlapping sequence. No parallel work streams, no shortcuts, no way to speed it up. By late January, executives were having whispered conversations in closed rooms. Conversations nobody wanted to admit were happening. Conversations about telling the Army they simply couldn't meet bomber production targets. Even worse, some feared Douglas or Consolidated might be brought in to take over primary production. But the truth was obvious. If Boeing didn't fix the wing bottleneck, they were going to lose the B-17 program entirely. Walk onto Wing Station Number 4 and you'd see the problem instantly. A massive 32-foot jig holding the wing's aluminum skeleton. 7 layers of carefully machined skin waiting to be riveted down. Everything began at the wing root, worked outward toward the tip. Straightforward on paper. A nightmare in real life. Each rivet row had to be installed in a strict order, row 1, then row 2, then row 3, because each row reinforced the previous one. Structurally, it made perfect sense. But physically, it guaranteed a traffic jam. To install row 1, a riveter worked topside while a bucker squeezed underneath through the wing's cramped internal spaces. They had to be perfectly synchronized. Miss the timing, and you created a loose rivet. Fixing one mistake took 3 minutes. Multiply by 12,000 rivets, and mistakes became catastrophic. Worse, row 2's crew couldn't start until row 1 passed inspection. And row 3 couldn't start until row 2 advanced far enough. So crews suited up, walked into place, and waited. Production wanted parallel work. Geometry made that impossible. You simply couldn't fit enough bodies around the wing to rivet multiple rows at once. Add to that the pneumatic rivet guns, industrial jackhammers shaking workers' whole bodies, plus heavy air hoses snaking across the floor like angry garden snakes. Workers constantly unplugged hoses, coiled them back up, stepped over cables, searched for new coupling points, and repeated that process dozens of times per wing. And then came the heat. 17 workers crowding one wing section, air hoses blasting hot exhaust, lights baking the aluminum skin, metal expanded microscopically, holes shifted out of alignment. Workers spent hours reaming just to make everything fit again. None of this appeared in the blueprint, because the blueprint imagined a perfect world. But Boeing Plant 2 was not a perfect world. It was loud, it was hot, it was rushed. And the design ignored physical reality. Which brings us to Frank Shamansky. He didn't look like the guy who was going to change the war. 31 years old, 5'7", hands permanently stained with aluminum dust. Before the war, he installed door panels at Chrysler in Detroit. Mind-numbing, repetitive work. But it taught him something. The rhythms of assembly, how people move, how processes flow, how bottlenecks are born. Frank moved to Seattle after Boeing began mass hiring, took the swing shift at Wing Station Order 4, and spent his nights riveting, sweating, waiting for inspectors, dodging hoses, and watching. Because Frank had a habit no one else had. He couldn't stop paying attention. While most riveters focused on the next rivet, Frank watched the whole dance. He noticed row 3 always waited for row 2. Row 2 always waited for row 1. Row 1 always waited on inspectors. He noticed fatigue setting in long before anyone admitted it. He saw the inefficiencies nobody else had time to see. And on February 4th, during a late-night break, staring at a finished wing section being hauled to final assembly, something clicked. The rivet pattern looked perfect, but only from a structural standpoint. From the perspective of someone actually building it, it was a nightmare. At Chrysler, they didn't assemble door panels from one edge to the other. They worked from multiple corners inward. It allowed parallel work. It reduced overlap. It cut time drastically. So Frank looked at the wing blueprint again and realized something bold. The wing didn't have to be riveted in straight rows. What if rivet work started from multiple access points simultaneously? What if the pattern wasn't linear at all? What if it followed the wing's physical geometry rather than the theoretical ideal? He grabbed a pencil, sketched a pattern, stared, crossed things out, tried again. What he created looked wrong, like someone had thrown rivets at a blueprint, clusters, radiating lines, irregular zones. But the more he studied it, the more it made sense. This pattern allowed 5 workers to rivet at once without crossing paths. He didn't know structural engineering, he didn't know stress curves or load lines. But he knew workflow, and he knew this would work. The only problem? Nobody at Boeing took suggestions from a grade 2 riveter, except one man. Frank worked swing shift, and his supervisor, Bill Hendricks, wasn't the usual follow the manual, keep your head down type. Bill had started on the floor himself as a sheet metal worker. He knew what it felt like to crawl inside a wing, to hold a bucking bar until your arms went numb. And unlike most supervisors, he listened when people further down the ladder had ideas. On February 11th, Frank caught him during the 8 p.m. shift change. The floor was still loud, but calmer than peak hours. Frank pulled out his time card, the back covered in pencil lines and strange clusters of dots, and showed it to Bill. Bill stared at it for a long time. "This goes against every structural loading principle Boeing uses," he finally said. "You know that, right?" Frank shrugged. "I know it's different. I don't know the math." Bill did. He explained that the traditional straight row rivet pattern wasn't random. It followed stress lines. When a wing flexes, under the weight of fuel, the engines, turbulence, tight turns. The stress doesn't spread evenly. It flows along invisible paths through the metal. Engineers like Theodore von Karman had already written the rules. Fasteners had to be placed to match those stress paths, or you got cracks, fatigue, and failure. The B-17's wing was built around that idea. Rows of rivets laid out to match predicted stress, densest where the loads were highest, looser where the wing carried less force. Changing that pattern wasn't like changing the order of tasks on a checklist. It was messing with the wing's skeleton. On paper, Frank's pattern was nonsense. His clusters hugged structural ribs. His rays of rivets connected those clusters by convenience, not stress path. If it worked at all, it would be by luck, not design. Bill walked him through the nightmare scenario. The wing might pass initial inspections. It might even handle a few flights. But under repeated combat loads, rough weather, emergency maneuvers, heavy bomb loads, tiny fractures could start. One crack, then another, spreading silently through the aluminum. And then one day, a wing snaps off at 15,000 feet. People die. Frank listened. He didn't argue. He understood the stakes. But Bill didn't stop there. He raised a question almost nobody in engineering had seriously considered. What if assembly efficiency is part of structural strength? He pointed back toward Wing Station 4. If it takes us 20 hours to build a wing, and we're exhausted, cramped, tripping over hoses, how many of those 12,000 rivets are actually installed perfectly? How many are just good enough because the bucker missed his timing or the metal expanded from the heat? What if your theoretically weaker pattern gives us practically stronger wings because the rivets are installed better? That was a dangerous idea. Up to that point, Boeing's entire mindset was simple. The blueprint defines perfection. If the factory can't hit that perfection, retrain the workers or fire them and hire more. You don't redraw the blueprint because people are tired. But Bill had seen too much. 18-hour wing assemblies, workers shaking from fatigue, inspectors quietly signing off borderline rivets because rejecting them would blow up the schedule. He knew the reality. Perfect on paper was not what was actually being built. So he did something risky. He folded Frank's sketch, slipped it into his pocket, and said, "I'll talk to someone." Frank went back to his rivet gun, fully expecting that to be the end of it. Bill did not go to the chief engineer. That would have killed the idea instantly. Instead, he went sideways to assistant production manager Donald Douglas. No relation to the Douglas Aircraft Company. Douglas was hanging on by a thread. If production didn't improve soon, everyone knew he'd be out of a job. Desperate people listen differently. On February 18th, Douglas glanced at Frank's sketch and dismissed it on sight. "This is garbage," he said. "Get it out of my office." But Bill didn't leave. He pulled out the real weapon, 6 weeks of time logs from Wing Station 4. Every wing, 19 to 22 hours. No exceptions. No hero crews going faster. No clever tricks. The bottleneck wasn't laziness or bad organization. It was designed into the process. Douglas studied the numbers. He wasn't an engineer, but he could do math. Even if this weird pattern was only half as good as Bill claimed, cutting wing time in half would be massive. There was just one huge problem. Boeing's head of engineering for the B-17 program, Oliver Eccles. Eccles was the kind of man who treated deviations from his blueprint like personal insults. If Douglas brought him an unapproved rivet pattern drawn by a swing-shift riveter, the conversation would end with Douglas unemployed and Frank reassigned. Or worse. But Douglas also knew something Bill didn't. The Army Air Forces were already looking at backup options. Consolidated was pushing their B-24 Liberator hard, promising easier manufacturing, faster production, higher output. General Arnold was listening. If Boeing didn't show serious improvement by mid-March, they were going to lose their position as America's primary heavy bomber source. Douglas looked at the sketch again. Then at the time logs. Then at the calendar. He made a decision that broke more than a dozen internal rules in one shot. He approved a secret test. No engineering sign-off, no official memo, no production meeting. Just a quiet experiment in the middle of the night, where nobody important would notice. He picked a wing section that had already failed quality control for unrelated reasons. A damaged spar meant it would never fly anyway. Perfect test subject. He scheduled the experiment for graveyard shift on February 21st, starting at midnight. He pulled 5 experienced riveters from swing shift, Frank included, and told absolutely nobody else. The test started at 12:14 a.m. By then, Frank had spent 3 days cleaning up his sketch. He'd color-coded zones. Red for worker 1, blue for worker 2, green, yellow, purple. Each color represented a cluster of rivets that could be accessed without interfering with anyone else. No overlapping spaces, no wait times. 5 people, 1 wing, full parallel work. On the factory floor, it looked insane. Traditional riveting had a certain rhythm to it. Row after row, marching across the metal, everyone moving in sequence. This looked like organized chaos. One worker was buried deep in the wing's main spar cavity. Another was under the trailing edge. A third moved along the top skin near the leading edge. They didn't follow rows, they followed clusters. To anyone walking by, it looked like nobody knew what they were doing. Douglas watched from 30 feet away, stopwatch in hand, burning through lucky strikes. Bill stood next to him, silent, eyes locked on the wing. Every 15 minutes, Douglas checked progress and scribbled notes. By the 2-hour mark, the wing should have been maybe 20% done. It was almost halfway finished. The riveters started realizing it too. Normally, they spent a huge chunk of time waiting. Waiting for inspectors, waiting for access, waiting for someone else to get out of the way. Now, they just moved to the next mark. Rivet, buck, move on. No traffic jams, no tangled hoses. They weren't standing in each other's heat clouds, so the metal wasn't expanding as much. The wings stayed cooler. The holes stayed aligned. The work just flowed. At 2:21 a.m., 127 minutes after they started, the last rivet went in. Douglas clicked his stopwatch. 2 hours and change? From bare framework to fully riveted wing section that normally took 20 hours. That was the first miracle. The second miracle was that the wing didn't look rushed. Douglas walked up and started inspecting rivets at random. He checked mushroom heads, edges, sheet fit. Then he called over Jimmy Chen, the graveyard shift quality inspector, and didn't say a word about what they had done. Chen ran his normal inspection routine: rivet spacing, thickness checks, tapping each head with a hammer and listening for the telltale sound of a bad one. After 40 minutes, he looked up and said, "This passes. Whoever did this knew what they were doing." Douglas told him the time. Chen laughed, thought it was a joke. Then he saw the stopwatch. Then he rechecked the rivets, because there was no way a wing built that fast could be this clean. But it was. And not just acceptable, it was better than normal. Chen, like most good inspectors, kept his own private defect log. On average, a standard B-17 wing had around 140 rivets that needed rework: loose, misaligned, or flawed. This wing had 11, not 1 and 11, 11, less than 1/10 of the usual defect count. That answered one question. Frank's pattern made assembly faster and cleaner. But another, scarier question remained. Would it hold up under real stress? Douglas knew they couldn't just bolt this thing to an aircraft and send it into the sky. They needed hard data, load tests, strain measurements, real numbers. So, at 3:30 a.m., still running on adrenaline and nicotine, he broke another rule. He called Boeing's structural test facility, woke up the skeleton night crew, told them they needed to perform emergency stress tests on a wing section. He conveniently forgot to mention that the rivet pattern was completely unapproved. They rolled the wing into Building 7 just after 4 a.m., mounted it into a huge test frame, and got ready to bend it until something broke, or proved it didn't. The structural test began just after 4:15 a.m. The crew locked the wing into a massive hydraulic press, a machine capable of simulating the brutal forces an aircraft faces in flight. They could bend the wing upward or downward with up to 150,000 pounds of force, far beyond what any B-17 should ever see in combat. The official Army Air Force's requirement at the time, Specification R-1816B, demanded that a wing survive loads equivalent to 6.2 Gs without permanent deformation. Anything less was an automatic failure. Douglas stood behind the safety line, exhausted, shaking, but laser-focused. He hadn't told the test crew what made this wing special. He just watched the gauges and waited. At 1 G, the wing behaved normally. At 3 G, still normal. At 6 G, the upper limit of what a bomber might hit during a violent evasive maneuver, the wing flexed exactly like a standard B-17 wing should. Then they crossed into forbidden territory. 6.2 G. Qualification threshold. The point where any hidden weakness, misplaced rivets, misaligned skin, structural imbalance should reveal itself. Nothing happened. Douglas swallowed hard and told the operator, "Keep going." At 7 G, the wing still held. At 8 G, strain started to show near the root, exactly where it should for a properly functioning structure. At 8.4 G, nearly 40% beyond the required limit, Douglas finally stopped the test, not because the wing failed, but because he was genuinely afraid of destroying the $1 million hydraulic press. When they released the pressure, something even stranger happened. The wing returned to its neutral position perfectly. No permanent bend, no visible deformation, no cracking. That shouldn't have been possible. A wing pushed past 8 G should show at least microscopic warping. This one didn't. Jimmy Chen ran another full inspection, checking every rivet that had sat under maximum load. None had loosened. None had slipped. It was as if the wing had been riveted by a team of master craftsmen working under ideal conditions. Except it was riveted by 5 guys following a pencil sketch on a graveyard shift. As dawn approached, Douglas stood staring at the wing in disbelief. The explanation slowly crystallized. Frank's pattern, random as it looked, actually supported the wing's natural load paths. By concentrating rivets near the structural ribs, he unintentionally reinforced the strongest parts of the wing. The radiating lines acted like auxiliary reinforcements, spreading stress more naturally than rigid parallel rows. In other words, the rivet pattern didn't fight the metal. It flowed with it. It was accidental engineering brilliance. By 6 a.m., Douglas knew he couldn't hide this. Someone higher up needed to see it. Someone with the authority to change Boeing's entire production process. Not Eccles. Eccles would kill the idea instantly. He went straight to James Murray, Boeing's vice president of operations. He woke the man at his home. Murray arrived at the plant at 7:15 a.m., wearing a sweater and weekend trousers, furious and half awake. But once he saw the data, the stopwatch times, the defect counts, the stress test results, his anger evaporated. He asked one question: "Can we train 200 riveters to do this by Monday?" Douglas blinked. He hadn't even thought that far ahead. He'd been focused on proving the concept. But Murray already understood the impact. If one wing went from 20 hours to 2, 42 wing stations could increase production by a factor of 10 without adding a single worker. And wings were the production bottleneck. Everything else, fuselages, tail sections, internal systems, was ready long before wings were done. Fix the wings, and the entire assembly line exploded with speed. So Murray made the decision. Over the objections of engineering, over the screaming protests of Eccles, over warnings about liability, safety, and legal exposure. He ordered Frank's pattern implemented across the entire production line. Effective immediately, February 25, 1942. He promoted Frank to production methods specialist with a $40 weekly raise. He promoted Bill Hendricks to senior supervisor. He told Douglas his job was safe, and he told Eccles that if he wanted to argue, he could explain to General Hap Arnold why Boeing was still producing 14 bombers a month while young American men were dying overseas. Results came fast. March 1942, 47 B-17s delivered. April, 91, June, 186. But July was the real shockwave. That was when all 42 wing stations had fully converted to Frank's clustered pattern, and the riveters had mastered the new workflow. July 284 B-17s, August 319. September 362 bombers in a single month, more than all of 1941 combined. This wasn't just a production miracle. It changed the war. By October 1942, the 8th Air Force launched its first mission with over 100 B-17s hitting industrial targets in Lille, France. The Luftwaffe was built to counter raids of 20 or 30 bombers. That many flying fortresses in one formation created so much defensive fire, it formed what pilots called a wall of lead. German fighter pilots described attacking those formations as suicide, and America would only send more. By January 1943, 300 bomber missions. By mid-1943, 500 bomber missions. Every one of those aircraft came from plants using Frank's pattern. The Schweinfurt-Regensburg raids in August 1943. Missions aimed at crippling German ball-bearing production required 376 B-17s. Without Frank's rivet pattern, Boeing wouldn't have built that many aircraft total by that point in the war. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had all adopted versions of Frank's method. Combined, they produced over 500 heavy bombers a month. The Germans produced more fighters in response, but they couldn't keep up. You can't win an air war when the enemy builds bombers faster than you can shoot them down. And nobody ever heard the name Frank Shamansky. He received a modest commendation from the War Production Board in 1943, a certificate signed by a man he never met. After the war, his job title disappeared in workforce cutbacks. He returned to Detroit, worked for Ford, raised his family, died in 1971, unaware that he had changed aircraft manufacturing forever. But he had, because engineers eventually discovered what Frank had stumbled onto: design for manufacturability, DFM. The idea that engineering perfection is meaningless if the design can't be built efficiently and consistently in the real world. By 1947, Boeing used Frank's principle on the B-47 Stratojet. The chaotic-looking rivet pattern that allowed 6 workers to assemble a wing in 3 hours? That was the Shamansky method, just without the name. Douglas Aircraft applied the same logic to the DC-8. Lockheed adopted it for the C-130 Hercules. The Boeing 707 used cluster riveting, a sanitized corporate term for Frank's accidental discovery. Today, the principle is universal. Aerospace students at MIT learn about the B-17 riveting problem as a case study in engineering philosophy. They learn that a theoretically perfect pattern produced an imperfect product, while a seemingly messy pattern, optimized for real human work, produced stronger, more reliable wings. Modern aircraft like the 787 use computer algorithms to generate rivet patterns that look random, but are optimized for both load paths and assembly access. Frank did it by watching tired workers and tracing pencil marks on the back of a time card. He didn't know the math. He didn't know the equations. He just understood people, tools, fatigue, movement, the reality of building things, not the theory of designing them. And that's why his story matters. It's a reminder that sometimes the person doing the work knows more about the work than the person designing it. That real-world knowledge, the kind earned through sweat, repetition, and paying attention, is as valuable as any engineering degree. Every generation has its Frank Shamansky, someone who sees the simple, obvious solution that experts overlook. Smart organizations listen. The rest keep riveting wings in 20 hours and wondering why they're losing. And so, when we look back at the B-17, the aircraft that helped turn the tide of the air war, we tend to see the steel, the engines, the firepower. But behind every fortress that climbed into the sky was a worker like Frank Shamansky, someone whose name never reached the history books, yet whose idea helped carry an entire nation through its darkest hour. His rivet pattern didn't just shorten production time, it reshaped how machines, teams, and entire industries thought about building the future. Frank never knew the scale of what he'd done, and maybe that's the beauty of it. History is built by people who never hear the applause. And sometimes, the difference between losing and winning a war is nothing more than a pencil sketch made by a man who simply saw a better way.